This video is not part of the IB syllabus, and it's on phase diagrams. A phase diagram is simply a graph, and typically it's going to be pressure against temperature. Though you could do a phase diagram for pressure versus volume, or you could do a phase diagram for volume versus temperature. But by far the most popular is pressure and temperature. So let's suppose right here on our graph represents 1 atmosphere pressure. Atmospheric pressure 101.3 kilopascals. Then of course, if we're at low temperatures over here, our substance is likely to be a solid. But as we increase the temperature, it's going to change into a liquid. And we increase the temperature a little more, it changes into a gas. Now this temperature right here, where it changes from a solid to a liquid at atmospheric pressure, we call that the melting point. And of course, this temperature here, where it changes from a liquid to a gas, we call that the boiling point. But now if we think about what happens as we lower the pressure. If we go to lower pressures, turns out you can't make a good cup of coffee on a mountaintop. And that's because the pressure is too low there. At lower pressures, the boiling temperature is lower. So you can't make a good cup of coffee because you can't get the water hot enough. So what happens here is effectively our boiling point decreases with temperature, something like this. That line represents how our boiling point gets smaller as the pressure lowers. And similarly, the melting point gets smaller as pressure lowers. And these two curves will eventually hit each other. And you've probably heard of sublimation and deposition, those instances when solids change directly into gas, such as with dry ice, or gases can change directly into solid. This occurs at low temperatures and low pressures. So down here is where we would see sublimation and deposition. Deposition when it changes directly from a gas to a solid, and sublimation when it changes directly from a solid to a liquid. And this point here has a special name. It's called the triple point. And it represents a very unusual situation. At the triple point, if you take a substance and get it at its triple point, you'll see some solid and some freezing going on. At the same time, you see some liquid and some melting going on. At the same time that you see bubbles taking place, producing gas because you've got boiling going on. In fact, let's take a few minutes to actually see what a triple point looks like. Right now you've got a liquid. You can see the solid forming. It's like an ice. And now you see the bubbles. So we've got solid, liquid, and gas all at the same time, all occurring at once, all in equilibrium with one another. That video is taken from the YouTube channel Coach K12. Now of course these two lines here will extend upwards, so we can go to even higher pressures than atmospheric pressure. And of course as we go from a liquid to a solid, we'd call that freezing. And if we go in the other direction, we'd call that melting. So if we're right along that line, any pressure and temperature right along that line, you would see an equilibrium situation where melting and freezing are taking place at the same time. And similarly over here, liquid to gas, that would be boiling. Whereas gas to liquid would be condensation. So anywhere along that line, we'd have boiling going on at the same time as condensation's going on, and there would be an equilibrium between the two. And it turns out that if you get your pressures and temperatures high enough, you can reach what's called a critical point. And once you're beyond that critical point, anywhere out here, you get what's called a supercritical fluid. Now remember, fluids can really be liquids or gases. So a supercritical fluid is something in which is something in which there's only one phase. The liquid and the gas phases are the same thing. It behaves like a liquid and a gas at the same time. Let's take a look at the formation of a supercritical fluid. This is taken from the YouTube channel Applied Science. What we're looking at is carbon dioxide. You can see the two separate phases, liquid and gas. Time-lapse photography, heat's being added, and right about now you've got a supercritical fluid. So it's neither a gas nor a liquid, it's both at the same time. So here's a phase diagram for water. So right here we're at atmospheric pressure, and of course that gives us our melting point of 0 degrees Celsius. And if we run into the other curve, of course here we get the boiling point. Up here at high pressures and temperatures we get that supercritical fluid where you can't distinguish between the liquid and the gas. The liquid and the gas are the same thing. Triple point is right here. So along this line here we'd have an equilibrium between sublimation and deposition. Gas changing into solid at the same rate that solid is changing into gas. So along this line here we've got an equilibrium between melting and freezing. Along this line we've got an equilibrium between boiling and condensation. And one other thing that's worth pointing out. If I draw a vertical line up from the triple point, for the case of water, you'll notice that this curve, it's bending away from that vertical line. And you also probably realize that ice is less dense than water, and that's why ice floats on top of water. And whenever you have a situation like this, where this curve bends to the left, that means that the liquid is more dense than solid. If it bends the other way, so maybe a more typical situation would be a curve like that, that would be the case where the solid, I think it's sort of expected case, where the solid density is bigger than the liquid density. So just one more thing that we can see from these phase diagrams. And as a final point, we talked about what makes an ideal gas an ideal gas. Well, basically you've got to get as far away from the liquid and the solid states as possible. So you want to be over here on the PT diagram, which means you want to have low pressure for an ideal gas. You want to have moderate temperatures, and overall, of course, you want to have low densities, or relatively low densities, so that those molecules are never very close together and they don't interact via electrostatic forces. And that's all for today, folks. Thank you very much.